Hi everyone, welcome to Data Umbrella's webinar. I am going to do a brief introduction and then I will introduce our speaker, and then at the end we'll have an open question and answer session. This webinar will be recorded and then it will be available on our YouTube channel in the next 24 to 48 hours. Data Umbrella is a community for underrepresented persons in data science, and we're a nonprofit organization. Here's the team. Here with me on the webinar is Reshama, who's the Community Manager and Director of Data Umbrella. We also have Christina, Sandra, and Sangam. We have a code of conduct and we are dedicated to providing a harassment-free experience for everyone, and we thank you for helping make Data Umbrella a welcoming and friendly community for all. You can support us in different ways. The first way would be following a code of conduct so that we can make this space welcoming and collaborative. You can also share Data Umbrella webinars with others, and then you can contribute to Data Umbrella and open source through contributing to our video timestamps through our new website, which is open source, where you can contribute to the code. And then we have the PyMC Sprint website as well. All these websites, all these repos can be found on our GitHub page, which is Data Umbrella. We also have a blog and events board where you can also contribute. The repos as well are on GitHub. You can also donate to a nonprofit. We are on Open Collective as Data Umbrella, and we're also on Benevity, which is a company-matched enable platform. You can also subscribe to our YouTube channel. We always post our videos where you can look at the video of this webinar after it's done, and you can also view other webinars that we have hosted. We have different libraries on our YouTube channel and playlists, including career advice, PyMC series, NumPy series, contributing to open source, data visualization, and scikit-learn. You can also sign up to our monthly newsletter. Our monthly newsletter is hosted on Substack, where we release our newsletter at the first of the month. We also have resources on our website, dataumbrella.org, where you can find resources on open source, guides to using inclusive language and allyship, accessibility and responsibility, AI ethics, and more. We are also on all social media platforms. You can find us on Twitter and LinkedIn. You can also find us on Instagram and Facebook. We have our website, dataumbrella.org, where you can access different materials. You can also follow our meetup page where we post events. We always have at least 2 events per month. This webinar has live captioning, which is on the menu of your screen, which is labeled CC. Feel free to use that while the webinar is ongoing. We have an online suggestion box. So this online suggestion box is where you can fill out suggestions for future events, feedback on this event, any technical issues if you have any during the webinar, and any other general feedback that you have for us. Upcoming events. So this month on 14th, we have another event on Intro to Julia and Libraries for Machine Learning and Data Science. In July, we have 2 events, Intro to Quarto and Machine Learning Visualization using Yellowbrick. All these events can be found on our meetup page, where you can subscribe to get notifications when we post an event. On today's talk, today's talk is an introduction to ImageIO, and our speaker is Sebastian. So Sebastian, for the past 2.5 years, has been the co-maintainer of ImageIO. During this time, he has architectured ImageIO version 3 API, added a new video backend, and grew monthly downloads from about 2 million to well over 15 million. In parallel, he actively contributes to various open source projects in and around the PyData ecosystem. He graduated with a PhD in computer science and is now working at Triplet, which he is part of the data team. You can find him on GitHub and LinkedIn. These slides are in our handout section, so if you need to find the links to his GitHub and LinkedIn, you can find them there. And with that, I will now welcome Sebastian to take over.
Beautiful. Thank you so much, Beryl. So Beryl already has given a nice introduction to who I am, so I will skip that part and jump straight into the talk. Right. So back from the start. Today, I will talk a bit about ImageIO, which is a library I've been maintaining for the past 2.5 years. And ImageIO itself is older than that. We've been around for roughly 10 years, but I'm the primary maintainer of this library for the past 2.5 years. And that's sort of the main time that I've been working on this project. Right. What I will talk about today is I will talk about ImageIO in 3 different parts. First, I will give you a general introduction into ImageIO. When we will look into like how does the library work, some examples of it, the API around it, when you would use it, and what kind of things it can do. Then, in the second part, I will look at the software architecture and the design of ImageIO itself, so that you know what's happening sort of under the hood as you use ImageIO, which is useful, for example, if you run into a problem and something doesn't work out of the box as you wanted. Knowing how things are structured under the hood helps you pinpoint where things might go wrong or how you might want to reconfigure some different parts of it to make it work in the way you would like. And then finally, I will take a step back from ImageIO itself and show you an end-to-end example of ImageIO, which sort of tries to put this into a bigger scope so that you can see, okay, here's an example of where I would use ImageIO in the wild. And in this case, it would be in a pipeline that does visual recommendation on apartments. Right. Jumping into it, the first part, I will talk about what is ImageIO. Now, in a nutshell, ImageIO is a library that converts between binary images, the binary format of images, and NumPy arrays. So the kind of images that you would have stored in your disk, and then we try to load it, decode it, and put it into a NumPy array, and also the way backwards. And the idea for ImageIO is to support this in as easy a way as possible for as many formats as possible, so that you can get an hopefully seamless interface between the Python layer and your raw data. And as an example on how you would use this, you would start out with just importing the library as you would normally do in Python. And a nice little flourish, if you will, here is that we have a namespace API. So in this case, you would import imageio.v3, and that would give you access to the v3 API. For the old one, which we still support, you would, for example, import imageio.v2, and that would give you the old API that has been around for longer. Right. Well, after importing, you would call functions as you would expect. And one example here is emread, which, as the name implies, reads images. So you call iio.emread, give it a path to the image, in this case, some JPEG, and then ImageIO will load the library and load the image and give you a NumPy array as a result. And then, yeah, as you can see, this is a standard NumPy array in the format you would expect. You get the number, height, width, and the number of pixels. And then if you wanted to write the image out again, there's a function called emWrite, which writes images. You give it a path to where you want to store the image, and you give it the array. And in this case, the file name ends with a .png, which is an indicator that you would want to write a PNG file. ImageIO picks up on that and then converts the image into a PNG file and then writes it to disk. And with these 2 lines, you don't necessarily need the shape. You would have converted a JPEG into a PNG. And that works for a couple hundred formats in almost anything you like, which is quite nice because that's what we're trying to achieve. Right. So why is this exciting, or why should you be excited about ImageIO? Now, I can't tell you why you should be excited, but I can tell you why I'm excited about it. The first reason is that it's quite widely adopted. Given that we've been around for quite a long time, there's a lot of places where ImageIO is used today. First of all, it's used pretty much all around the world. Like this picture in the bottom here, I've got that one from our documentation. We have sort of a very loose ability to see which country people are from when they call the website of our documentation. And this is just a co-play of the distribution over different countries. And as you can see, it's used pretty much everywhere. The second thing is that we have quite a large user base. So at the moment, we're sitting at like slightly above 15 million. When I wrote this talk initially, we were sitting at like 18 million. This number always goes up and down depending on how well people cache their dependencies. But this is roughly sort of the number, which means that if we do something that breaks somewhere, then usually we get informed quite quickly. So any bugs that do occur get reported quite quickly and then get fixed quite quickly as well, which is nice. And then finally, there's quite a few dependencies that are large that now depend on ImageIO, which is quite cool. First and foremost, scikit-image, which you've probably heard of. So every time you do, for example, skimage.io.emread, that one actually calls ImageIO under the hood. Then if you're into like machine learning on images, you have weights and biases and abominations as 2 of the 3 big pre-processing libraries. they depend on ImageIO. You have MoviePy, which mostly focuses on movies, but can also load images. And under the hood, that is done through ImageIO. And then you have Napari. So if you're in like the biomedical field, then you probably know that library as well. That one also uses ImageIO. And then there's also SciPy. There's a kind of a funny story there. SciPy used to have an EM read function, but then they realized that there also is ImageIO, which tries to just focus on reading and writing. And that seemed to, they thought that we're doing a good enough job that it doesn't make sense to reinvent the wheel. So they deprecated their EM read feature, and now it's all just asking people to use ImageIO instead. Right. And the other reason is that ImageIO is quite feature complete at this point. You get it through all the major channels, pip, conda. You can even do now an apt-get install ImageIO. Although, of course, as with any other Python package you get through apt-get, it is a bit out of date. So if you want the recent version, you would preferably use pip, maybe Anaconda. And then also, if you use Google Colab, ImageIO is installed by default. Although, again, the version tends to be a bit outdated. So if you want the recent version, go through pip. Then we support roughly 250 image formats and 100 some video formats. And the example that I showed you before, where you would like convert a JPEG to a PNG, the same thing works with video formats. And that's quite a nice thing. And then, of course, performance-wise, we're roughly on the same level as PyTorch, a bit slower than Pill on JPEG specifically, because Pillow is the best library to load JPEGs at the moment because it's the fastest. So internally, we delegate to Pillow because that's the thing that makes the most sense. And then the difference there is essentially overhead, which, by the way, is the same thing that PyTorch does under the hood. So that's why we have roughly equal performance for JPEG specifically. Right. Another thing that is cool about ImageIO is that ImageIO is quite hacker-friendly. So for example, if we want to, for whatever reason, turn a webcam stream into a GIF, we could do that quite easily. Now, I should give a disclaimer here. GIF is not a video format, so doing this will result in a really, really large file that you can't really share, and it's probably not the wisest thing to try and create like a 60 FPS GIF from a webcam, but just for argument's sake, you could hack it so that it actually does this. So the way you would go about this is you would import ImageIO as before, then you would call the function iio.emiter, which, as you might expect, iterates over images. And as target, you would specify video 0, which is, in this case, your webcam. And what this does is it opens or it connects to your webcam, and then it loads frames one by one as an iterator. And then you can use this iterator like any other Python iterator. In this case, we wrap it in an enumerate so that we can get the frame count as well. And then we just count a number of frames until we have collected, in this case, 150 frames. And assuming we run at 50 frames per second, that's roughly 3 seconds worth of video data. And then we store those in a list of frames. Once we have this list of frames, we write it as we have seen in the previous example using emWrite. This time we specify a GIF. We specify the duration, which is a flag for GIF that says how much time passes between 2 consecutive frames in milliseconds. In this case, 1000 divided by 50, which is 20 milliseconds or roughly 50 FPS. And then loop 0 means we should just want to loop that GIF over and over again. And with that, we have essentially converted webcam images to a GIF. Another cool example of the ImageIO is that it's actually quite elegant to use because it allows you to solve a lot of use cases in 1 or 2 lines. So the example that I have here is using it together with FastAPI. For those of you who don't know what FastAPI is a library that allows you to very easily build RESTful APIs in Python. So you would build something called a FastAPI app and then define certain endpoints. Like, for example, here with the apt.get/randomImage. And what this does is once you have started a web server that you have pointed to this app, you can then call the location of the server, like, I don't know, example.com/ in this case, randomImage. And then what FastAPI does, it will run this piece of code and then take the result of it and return it to you as normally a JSON file. But in this case, we overwrite it as a media type image and JPEG. So we would want an image back. And then what we do is we use ImageIO to then take our NumPy array, which represents the image, and encode it. And what happens here is that in the first line, we have image equals random rng.integers. So we generate some random numbers which represent our image. And then we write with emWrite those images to the special target bytes, which means we want to have a byte string as a result of this operation, which we then, because bytes don't have an extension, so we can't automatically infer it, need to tell ImageIO that we want, for example, in this case, a JPEG. And the way we do that is by adding the keyword argument extension equals JPEG. And then we get a byte string as a result, which we can then return as an image, as a JPEG image. And the cool bit here is that this doesn't touch your hard drive at all. So this happens completely in memory, which means you can do, for example, things like storing this function in a AWS Lambda callback, and then it will just work because it doesn't use the hard drive at all, which is neat. Right. Now that I've told you a bit about some examples on how you can use ImageIO in a nice way, here is the API. And the way I would approach this API is I would think of it as two separate parts. You have a high-level API, which you have seen a lot of the functions of already. You have emRead, which reads images. You have emItter, which iterates over images. This one is particularly useful for in cases where you have containers that store more than one image. So for example, TIFF files, GIFs, APNG, various videos, and so forth. In this case, emItter gives you images one by one. You have emWrite, which writes images, and then you have emProps for standardized metadata. I have not shown you metadata yet because metadata on images is a slightly more complicated topic because it gets quite specific quite quickly because each format specifies their own little set of metadata and they're not so easy to standardize. But to the extent that we can standardize them, you can access those standardized properties with emProps. And then the second part is the low-level API, which in this case consists of two functions, imopen and emmeta. And imopen gives you access to the plugin underneath that is used for that specific format to load. And what that enables is that you can, within the plugin itself, you can access the high-level API functions themselves, plus potentially a set of additional functions that are specific to the backend or the format. So for example, for video, when you read and write video, you can access specific functions that make sense for video, but not so much for images in general. And then you can potentially customize your use case to enable certain types of applications that would otherwise be hard to implement. Usually, or I would say like in 80% of the cases, this is not needed and the high-level API is perfectly fine. But in case you need it, it is there. And then you also have emmeta, which gives you access to the raw file format specific metadata, which is nice because, as I said before, various different formats specify their metadata in very different ways. And sometimes it's not so easy to say, okay, this field is equivalent to in one format is equivalent to this field in another format. So then rather than standardizing, emmeta gives you sort of, for this specific format that you're reading, it gives you the metadata in the format that the format specifies. Right. To make an example of imopen, we can use ImageIO to, in this case, write video incrementally. And the way we do that is we start by using imopen, which I said is useful in some contexts when the standard high-level API is not sufficient to describe what you want to do. And for writing video, for example, this happens in the scenario where you want to write large video files because uncompressed video is really, really big. So if you have even if you have a strong laptop with like 16 gigabytes, 32 gigabytes of memory, that is usually not sufficient if you want to write videos that are high quality and then like 30 minutes, 1 hour long. So in this case, you would want something that doesn't have to have the entire video in memory at the same time. And instead, you would like something that just has 1 or 2 frames in memory at the same time and then just loads them, does something to them, stores them in the new file. The way you go about this is you open the file. In this case, it's quite analog to like the standard Python open function. You do imopen, you specify the location, W stands for write, and then plugin is a keyword argument that specifies which plugin I want to use. Normally, imopen has the ability to automatically select the plugin depending on what type of resource you're trying to open. But you can also specify the plugin directly to avoid selecting a different plugin or to just control which plugin is used in the end. And in this case, opening it with PyIV gives us access to the PyIV specific API, which in this case allows you to do a file.init video stream, which initializes a new video stream in the file. In this case, we want it to be encoded as a libx264, which is one of the many formats or ways you can encode video. We want to write a 5 FPS video stream, and the pixel format is gray images, gray frames. And then from there, we write files in a way we've already seen. We use emiter, which loads frames one by one. So it's quite efficient because, as I said before, decoding the entire video can be very large. So doing that one by one is nice. And then we potentially add our code, for example, via scikit-image to transform the image in a way we like. And then finally, we write the frame out to disk. And then because we've used imopen in a context manager with with, we can just end the function there, and then Python or ImageIO will take care of finalizing the video in the end. Right. And then finally, to round this off, a short list of other cool things that you can do with ImageIO that can make your life easier. First of all, emread itself has a keyword argument called index, which allows you to specify specific images in a file. So I've said before that some containers are capable of storing multiple images in the same file. For example, videos, GIFs, APNG, and so forth. And if you want just one frame from this collection, you can specify an integer, and ImageIO will give you that image at that index. The other thing you can do is you can specify the ellipsis as an index. The ellipsis is the 3 dot symbol in Python. It's a cool backstory there, and if anyone is interested in the ellipsis and why it exists, I can tell you about that later. But if you use this as the index, as a parameter for index, you'll get a batch of images. So ImageIO will load all the images that are in the file, add a batch dimension as the first axis, stack them together, and give you the batch result, which can be useful, for example, if you load a GIF and you want all the frames of the GIF, then you can use the syntax to just get a block of image data and then process that one in one go. Another cool thing is that you can load URLs directly, so you can just pass in a link to an image, and assuming you can access that image without a password, you can just load it directly. Also, the same works for like anything that derives from IO base. So if you have a stream, a IO stream, a custom class that implements read, write, get line, and so forth, seek, and so forth, these will just work fine in ImageIO. Another cool feature, I've already mentioned the second point, the plugin equals argument, which allows you to select plugins directly. But what you can also do for the Pillow plugin specifically is you can specify a mode keyword argument, or rather, all keyword arguments that are not part of ImageIO's API itself will be forwarded to the backend. And in the typical case where you write the common formats, read, write, PNG, JPEG, GIF, those are probably the main ones, maybe TIFF, you can specify a mode argument, which then specifies the color format, and then ImageIO will use, in this case, Pillow, to convert the image from whichever color space it was in into RGB before returning it. So this way you can, even though you might have if you have a collection of images, some are RGB, some are RGBA, ImageIO will then sort of unify them and just give you RGB in the end, which makes a lot of input pipelines more consistent. Right, and this is the first part of the presentation. If you have any questions, let me check if there's already some in the chat. No. I will wait a minute or 30 seconds if there's any burning questions. Otherwise, I will continue with the next part.
Sebastian, there's one question, which says, what was the reasoning behind choosing FastAPI over Flask for this demo? I've only used Flask for Python, so I'm glad to learn more about FastAPI.
There's a couple of reasons for this specific presentation. The main reason is that it's shorter to write something in FastAPI, so I can write it in FastAPI and it still fits on the slide. That's the main reason for FastAPI in this case. The other reason why you might want FastAPI over Flask is that FastAPI is built on the asynchronous protocol, so on iSyncIO, which allows you to be more efficient and run things faster than pure Flask. Although, yeah, I guess that's a good answer. Right. Okay, other questions?
No, there's no other question in the Q&A. You can just go ahead, yeah.
Then I will continue. Right. The next part is, how much time do I have left? Okay, I will jump over this part because of time constraints. We can come back to this if you want to learn more about the design itself. And I will actually go straight for the visual recommendation engine, because I think this one is quite cool, but it needs a couple of minutes to unpack. Right. So what I want to do here is I want to show you how to use ImageIO in a broader context. And the context here is visual recommendation. And the first question to answer is then, what is visual recommendation? So in essence, visual recommendation is measuring how related two images are and then recommending similar items based on the similarity of the image. One example of this that you see in, for example, on shopping websites for clothes is that you have this like complete the look advertisement, and then you see different products that sort of relate to the image that you're looking at, and then you're trying to then they try to upsell you by suggesting the correct products. This is oftentimes curated by hand, but you also now see machine learning approaches to picking out the right products to match with this. And if you do that based on the image itself, then you would use visual similarity. Another example is visual search. So if you, for example, have ever used Google Lens, where you take a picture of something and it tries to find that thing online. So for example, you take a picture of a dress, it tries to find it online so that you can buy it. That's visual similarity or visual recommendation. And then what we're focusing on today is trying to find similar apartments. So if you have, say, a website, a marketplace that lists apartments, and you are curious on like, is there something that looks similar but potentially less expensive, then visual similarity between those two apartments could be used to find similarly looking apartments and then suggest them. So how would we go about building such a thing? Now, this slide is a bit intimidating, but I will unpack it piece by piece. The way the place we start is in this big blue box that I've labeled production. Now, this doesn't mean that this is the actual representation of the production system. What this means is like, this is the minimum viable block of things that we need to put together to build something useful that we can then use to then deploy and actually get what we want out of it, which is that we have various different apartments, and then we can go in and find similarly looking ones. And yes, so what we do is we start with an active apartment. Maybe actually, let me do this. Let me quickly stop sharing my slides and try resharing my entire screen. Because then I think this makes it more concrete if I do this. Yes, infinite recursion. If I do this one, right? So this is an example of a website where this might be useful. This is Blocket, which is a Swedish website for buying and selling various things. And they also have an entire section on finding apartments. So for example, I can go into this website and then you see various different apartments being listed here. And one thing, for example, that you can do with visual recommendation is you could try to look at the history of what people have looked at in the past, and then try to find similarly looking apartments and then just suggest them on the side here, right? And then, or if you click on a listing itself, this is how the listing would look like. You have a couple of pictures, you have the description, you have some descriptions of the apartment, you have the pictures, but then at the moment there's nothing here. But what you could add is like a widget of like, would you be interested in other apartments like that? And building something like that, that's sort of what we're after here. Right. And this is how, if you wanted to build this, these are the building blocks you would need to make this all happen. Right. So you would start with an active listing that the user is looking at right now, or something that you think the user has looked at in the past, and you would want to find similarly looking ones. And you start with a couple of filtering settings for that apartment. Because, for example, if I am looking for apartments in New York, there isn't really much utility in suggesting apartments in Boston because the user is not interested in those. They just want to see something in New York. So filtering on those settings is a necessary thing that we need to keep being able to do. Right. From these active listing, we get a bunch of pictures. And from the filter settings, we can query our database, and then we can filter out apartment listings that are relevant in general. And from these listings, we get those pictures as well. We can then take these pictures and put them into something called an embedding network. And what that does is it takes the image, puts it into a neural network, and then spits out something that we call the descriptor. And this descriptor has the property that similarly looking images are close in the resulting feature space. So a descriptor is essentially a vector of numbers, and pictures that look similar have similarly numbers in similar places. And with that, we can then establish a notion of like how similar or distant are these pictures. And then we can For 2 individual pictures, that's enough. We get a number, and the smaller the number, the more similar the pictures are. But apartments usually have more than 1 image per apartment. So then we have multiple images that we need to compare with multiple other images. And then we do that in the same way as you do in NLP, which is something we call an attention layer. And I can talk more about that if that is interesting. But for the purpose of this discussion, it's a thing that we can put in 2 sets of images, and it spits out how similar these 2 sets of images are. And then we can do this for all the apartments in our potential list that are currently available versus that one apartment that we're looking at right now. And then we get a list of numbers for each apartment in our current offerings or in our current database that tells us how similar they are to the current apartment. We can then sort by that number and select the top 3 or 5 apartments. Right. To make this all happen, we need to get this model, this embedding from somewhere. And the place where we get it from is from our model zoo, which is like a collection of machine learning models that we have trained in the past. And then we select the most fitting one, usually the current one that we're interested in. Now, to train this model, we need this green box here that I highlighted. We need, first of all, some amount of training data, which we can get. I will talk about how we get this in a second. And then we use a technique called tripleting. I will very briefly mention how that works on the next slide. And then one easy way of getting where we want to be is we use the process called fine-tuning. What fine-tuning is we start out with a foundation model or like a pre-trained neural network that is good on something. Usually what people use these days is something, for example, like a ResNet 50 is an old one that is an old established published model that can classify various categories of images. We take that one, we replace the classification head with this attention head that I mentioned earlier, and then we train the model on the images that we have collected in our training data, and then hopefully it will learn how to classify images in a similar way. And to create the training data that we need to actually train the model, we need to load the data from somewhere. If we have access to the full database, then we can just use that. If we don't have access, because we are not the owners of a website that happens to list apartments, we can load it from other places, like, for example, through web scraping. And what's important, what's interesting in this entire figure is that all the places that I marked in yellow are places where ImageIO can help you, but also those are places where images essentially pass either over the network or from one hard disk to another, or from the hard disk into our CPU for processing. So, for example, from the data loading part, we have the web scraper that then loads the image from the internet and stores it in a database, or we go from one database to another in the point 3 over here. And what I want to do is I want to look at 3 parts of this. The first one is the web scraping part itself and show you what ImageIO can do there. The second part is during this loading of the training data for fine-tuning. And the second part is in the process of building the training data in the first place from a history or collection of a lot of images. Right. Yes. So the first thing is loading the images. Right. When we load the images, I mentioned before that ImageIO can load URLs directly. And if we look at the website, the one that I showed you earlier, you will see that if you dig into this and explore the website, you will see that the image itself just traces back to some URL on the web, which is an S3 bucket, which is a URL which we can put directly into ImageIO and then download the image in the way we want. And the way we would do this is using this snippet down here, which only contains parts that we've already seen, except for one, not except, but like there's one cool thing about it, which is nice, which is that we can specify the output path as JPEG, and then whatever the image is, if it is a PNG, a GIF, a JPEG itself, whatever, it will convert the file into a JPEG and then store it. And that is nice because JPEG is a quite efficient format. So even if we store a lot of images, it will still only occupy a small portion of your hard drive. And secondly, a lot of foundation models that are trained on image data are, like, for example, ResNet 50 that I mentioned earlier, are actually trained on a lot of JPEG images. Now and that's nice because if we then feed it with JPEG images, we avoid a potential distribution shift between PNGs and JPEG because they tend to have slightly different artifacts. Most of the time that's not important, but sometimes it can throw the classification a bit. So now we can just avoid it and then store everything directly as JPEG. Right. Then for the second part, which I will go into in a second, we want to train the model. Once we have this data set, we want to train it using something called the triplet loss. Just for context, the triplet loss uses 3 images to train rather than, sorry, I need to take a step back here. Normally, when we train a model on images, we solve a classic classification problem. We have an example image with a label, and then we have the label. We can use that label to say, okay, what is the output right now versus what should the output be like? And then we can adjust the output of the neural network to match the desired output a little bit closer. For image similarity, that isn't necessarily always easy to do, because it's not always easy to say, okay, these 2 images should have a distance of 0.5, whereas these 2 images should have a distance of 0.8. So instead, what we do is we take 3 images, whereas we use the first one as an anchor point. The second one is something we say, this image is similar to the previous one. And then we use a third one, which is a negative image, and we say this image is kind of dissimilar to the first one. And then we put all these 3 images through our neural network and see where do they land in this embedding space that I mentioned earlier, and how is the distance between those 3 points. And if the distance between the anchor and the positive image is large, or larger than some threshold, then we try to change the weights of the neural network to make this distance smaller. Whereas if the anchor point and the negative example, if that distance is too small, smaller than a threshold, then we change the weights to make that distance larger. And this way, we can slowly but surely pull all the similar images in our feature space closer together, whereas all the dissimilar images get pushed further away. And that is a very cool idea. The problem is that PyTorch doesn't allow you to use this kind of loss or data set out of the box. So you need to write your own code to make this happen. And the way we write this code is, the important bit is, for those of you who have never used PyTorch before, if you define a data set in PyTorch, you need to define 3 functions. The first one is the initialization function. How do you set up the data set, which is not so important here. The second one is the length function. How many items are in your database, in your data set. The third is the important one, which I showed here, which is the getItem function, which allows PyTorch to say, give me the 90th image in the data set, and then your data set needs to figure out what are the necessary steps to take in order to load this example and return it to PyTorch so it can do the machine learning on it. And since we have a list of images, we can group them together in groups of 3, for example, by just classifying them. There's different ways we could classify them. One of them would be, for example, to say, okay, we have images from the same apartment and we have images from a different apartment. And obviously the images from the same apartment, we assume that the images from the same apartment are similar, so we want them to be closer together, whereas images from different apartments should be further apart. Another way you could do this is you could say things like, maybe if you have pictures of living rooms, those are more similar than pictures of bathrooms are more similar, and a picture of a bathroom and a living room, they're dissimilar. So you get to experiment with different hypotheses there and see which one works. But ultimately, what this results into is you specify 3 images in your database that you then want to load. And the way you load them is you do a you do IIO.emRead on the image. And so this is how you would go about loading it. Right. And then finally, the third part is how would you actually go about, I have this large history on of images. I select a subset of them and want to do machine learning on them. Is there anything smart that you can do? So the first naive approach would be to say, okay, we just copy the image, we just copy all the data from the history one-to-one into our database, data set, and then we use that as for training. This works, but what you will find is that you get IO bottlenecked by your training pipeline itself gets IO bottlenecked because images in the wild come in all different shapes, sizes, forms, etc. So then a lot of time when initially loading the image is spent on transforming that image from its initial size into a standardized size so that you can actually stack them together and do machine learning on them, which is something that you can avoid by just loading the image once in the beginning, reshaping it or resizing it into the form that you actually, and through the dimensions that you want, and then saving it again. And this is something that is super easy to do with ImageIO and scikit-image. And I will skip over how you would do that. But if you do that, what you will find is then now you don't have to do this anymore. And for my training setup, for example, I guess I'm running a bit low on time, I'm sorry. For my training setup, what ended up happening was that instead of having roughly 68% GPU utilization, which is the bottom line, so of like reshaping the images as I load them, I was switched into having 99% GPU utilization. So then this way, I would call this like baking in certain transformations into your data set, which is something that is quite easy to use to do with ImageIO, because you can just load the image very easily, apply the transformations, and then save it again. Right, and these are the 4 places. Summing up, there's sort of, in this example, there's 3 places where ImageIO can be really useful. The first part is sort of while building and collecting a data set for your experiments, especially if you're like just a hobbyist rather than having access to a big database of pre-existing images. There it's very useful. The second one is if you need to write a custom data loader API. There you can very easily rely on the building blocks that you already get from ImageIO to like load the image and prepare it. And then thirdly, you can speed up your training in certain cases by just baking in certain transformations in the beginning. Right, so these are the things that I've prepared, and now I'm happy to take questions again.
Thank you so much, Sebastian. We can now write our questions on the question and answer section or in the chat, and then Sebastian will answer them.
All right, there is a first question in the chat already, but I'm going to drink some water first. Right, so the first question is, are you a NumFocus project, and how are you funded? Right, so at the moment, ImageIO is not a NumFocus project. I would like to become NumPy affiliated sooner or later, but that is something that's currently in the making. That said, ImageIO is quite close to PyData and the umbrella around it, because it's sort of like it got created out of the observation that scikit-image was building its own I/O backend, SciPy was building its own I/O backend, and then various other libraries were doing the same. And it seemed like there was a lot of reinventing the wheel going on. So then people came together and said, well, maybe we can just make a library that just focuses on image I/O, so the I/O part, and then everybody can depend on that. So it kind of was created from that, but that was before NumPy and PyData was really that renowned, and everybody was aware of it. So then we never became part of it, but this is something we are looking into becoming at the moment. Are you currently, I just got a pop-up that asks me in a poll if I'm currently using ImageIO. I guess my personal answer is yes, I am. Right. The next question, what is the best way for the community to connect with ImageIO, platforms, etc.? So at the moment, the very best way is to go on to GitHub and open an issue and start discussing, especially if you want to contribute. And yeah, so there is that's one way. Another way is there is a Discord which is called Scientific Python, I believe. And on that one, I monitor that one as well. So there you can just reach out with questions, and then I will answer them and then get in touch. Yeah. And I also just realized there's a second part to the first question, which I didn't answer, which is how are you funded? So at the moment, we are able to accept, we're mainly funded through donations. There's 2 streams through which this is happening. One is Tidelift, and the other one is GitHub itself, GitHub sponsors. And at the moment, the only way of funding that we actually get something is through Tidelift. So if you want to support us, those would be the 2 channels through which you can reach out. And then a third question, how large is your team of developers? So we used to be 2 core maintainers, the person that originally invented or that started the project, and myself. And at the moment, that person has gotten 2 kids. So one of them is a newborn, so he is very busy taking care of the newborn baby. So at the moment, it is mainly me who is maintaining the library. But then we also have a lot of new contributors that do like 1 or 2 contributions and then help the library that way. So that's our main base of contributors. Where can we get a copy of the slides? I can send them to Beryl in the end, and then you can get them that way. I think that's a good way, if that works for you guys. Yes, and then finally, another question: do you collaborate with scikit-image developers? Yes, I do. I actually have a couple of pull requests in scikit-image itself. For example, there is a filter, the rolling ball filter, and I'm the one who actually wrote that code initially. But also the other way around, if there's any issues, the people in scikit with especially the loading, then the scikit-image people reach out to me, and then we fix that. Or if there's something that I find in the library that I would like to have, then I just ask them. Okay, another question. This might already have been mentioned, so apologies if that's the case, no problem. Do you anticipate any applications for video streaming? Oh, that's a good question. So I haven't touched on this in the talk, but I do have a slide on this, which is video streaming itself is possible in a limited fashion. And let me go to the slide. Do I have a specific one? I have this one. So video streaming itself is something that I would like to do. So you see in this slide on the roadmap, there's a point that says request refactor. And then in the second bullet point, it says support for video streams. And the backstory here is that the front end itself is quite agnostic. So you could potentially pass in a video stream. The back end itself, for example, PyAV, already supports video streams. But in the middle, there's one building block that currently filters out certain protocols, or it only allows protocols that it recognizes, which at the moment are the file system and HTTPS. And some video streams need specific other protocols, which it will just say, I don't know what this is, and then it will fail. So if I manage to find the time to do that refactor, then yes, we will be able to support video streams. If for now, the main things that are supported are streaming from your webcam. So that is, in a sense, a video stream. And the other one is, I think, Dash videos, because they use the HTTPS protocol, so they will work just fine. Right. Right. Are there tutorials for folks? Another question. Yes and no. There is quite a lot of extensive documentation. Am I still sharing the entire screen? No, I'm not. Otherwise, let me reshare my entire screen, and then I can just show you where to find this. Right. So if you go to ImageIO.readthedocs.io, which is our documentation, there you find all the information that you want. First of all, we have a list of examples, which is a quite extensive list of some of the examples that I showed you before, but also many, many more on how you would read and write images in various different formats. And that can get you started and show you a lot of the for a lot of cases where you would typically want to use ImageIO or another library that can read images, there are snippets that you can use to actually get the job done. And then finally, we have the API reference in the menu, which then gives you a narrative introduction here in the core APIs through the various APIs that we have. So it walks you through, okay, these are the functions, here's how you would use them, and here's the detail on what it all means. And that's, I think, the two places that I would use to start breaking into the library and reading up on it. But then there's no specific course series on how to use ImageIO. Right, another question. Do you have an idea of which industries mainly use ImageIO? To some extent, yes. I mean, I should put it this way. The main problem is that one nice quality, which also is a problem for me specifically, is that ImageIO is free and open source, and therefore there's no explicit tracking or usage analysis or anything happening, which makes it difficult for me to figure out who actually uses the library, which is a bit sad because then it's hard for me to figure out which parts are used or not. But it also means that the way I primarily discover who uses the library is by looking at who reports that they have problems with the library by raising issues, or who suggests new features that they would like because they like ImageIO and they would like a certain new feature to be added. And based on this information, the majority of people that use ImageIO are either in the scientific field, so they're like biomedicine people that use it for example, microscopy or analyses like that. But also, I've seen physicists use ImageIO. There's this funny thing which I found, which there's a paper citing ImageIO, and they do deep space telescope. They look at deep space images through telescopes, and apparently they do image processing, and in the process they use ImageIO, so they cited us, and that's kind of cool. So that's the one group. The other big group that I've seen are actually people doing video editing or photo editing, because they sometimes ask questions on how do I do this, how do I do that.
So Sebastian, thank you very much. It looks like those are all the questions that we have. It also, looking at the poll, I know when we spoke earlier, you mentioned that one of the things that you were curious about was whether, how people use ImageIO, which features they use most often and all of that. It seems like most of our attendees right now have not used ImageIO before, so want to learn about it.
Yeah. Interesting. This is also another thing that is quite true that I've noticed, is that a lot of people using ImageIO are not necessarily aware they're using it, because it ends up as a transitive dependency. Like, for example, and I talked about where ImageIO is used. Like, for example, here, you for example have scikit-image. So if you are a user of scikit-image and you use scikit-image.io, you are using ImageIO, but it's sort of under the hood, so you might not necessarily be aware that you're using ImageIO. Just as an interesting comment.
Is that information from GitHub where it shows the dependencies of like how many GitHub repos use a certain package?
Which piece of the information? Which packages use ImageIO?
Yeah.
Yes, that one is, yes, by me looking at who has reported that they had issues with ImageIO, and then I looked at the repository, and then, for example, if you look at the repository, there usually is, if they use setup tools, for example, there's either a setup.py file or a requirements file, and then in there it says ImageIO as a primary dependency. That's where I got this information. You're muted.
Thank you. Thank you so much for the presentation. Thank you, everybody, for attending. This is being recorded and will be on our YouTube within a couple of days. If you have any more questions, you can ask on the video comments. And once I get the slides, I will also include a link to the slides in the video description as well. So thank you for that. And with that, I'm ending the webinar.